Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jin Kim, and today we'll learn about the emperor of all maladies, the king of terrors, cancer. Let's get started. When it comes to illnesses, few words invoke the level of dread, despair, and doom as the C word: cancer. It's one of the biggest worries people have when they have unexplained symptoms, such as a lump under the skin, unexplained headaches, or blood in the stool. It's also one of the last things people want to hear from a doctor when they come to the emergency department. Yet, unfortunately, cancer is surprisingly common, to the point that I'm sure that every one of you listening to this episode either knows someone who has been diagnosed with cancer or lost someone to cancer. Heck, some of you may have personally had or have cancer to some degree. I personally have a deep history with cancer, as my father had cancer twice, and I have an about 90% chance of developing bowel cancer thanks to the magic of genetics. Yippee! Not to mention having close friends and colleagues either having survived cancer in younger days or battled against it in more recent years, and the sheer number of people I've seen have their lives changed through cancer through my work. So in today's episode, I won't talk too much about the emotional and social impacts of cancer, because I'm sure you all have personal experiences from your own lives and those around you. Instead, we'll focus on the medical facts so you're more prepared knowledge-wise if you were to come face-to-face with this awful malady in your future. We'll talk about the what, where, who, why, and how of cancer, from cell division to chemotherapy to oncogenetics to why it's so dang difficult to cure cancer. The tone will also be generally more serious and less bombastic than our usual vibes on this podcast, but that will be back in February with more cheerful topics, I'm sure. Still, I apologize in advance if I say something that is insensitive or potentially hurtful to you while talking about cancer, because my intent with this podcast, first and foremost, is being educational and helping people learn more about the world. So, without further ado, let's explain what cancer is to you as if you're a child. Have you heard of the mythical Hydra? It was a terrifying beast from Greek mythology that couldn't be killed. If you cut off one of its many heads, two would grow from the same place. The more you cut, the more heads would grow until there would be a giant tree of Hydra heads. It took the hunky hero Heracles, brawn and brain, to realize that he had to stop the heads growing back by burning the stump as soon as he'd cut a head off. But what if I told you that your body had the same fearsome power of growing back as the Hydra? Your body is a giant Lego structure made up of individual blocks called cells. Most cells in your body have the ability to grow and split into two to copy itself. This is how you grow from a peanut-sized teeny tiny baby in your mother's womb to the size that you are now, and to however tall you will be when you finish growing. It also means that when you hurt yourself, like getting a paper cut or scraping off the skin on your knees when you fall, your body can grow more skin cells to patch it back up, just like the Hydra. Now, this sounds awesome in theory, right? But if it's actually true, how come we don't grow to be 20 meters tall and with 6 arms and 3 heads and whatnot? What makes us stop growing after a certain point? This is because as much as we need cells to grow and divide for us to become adults, we don't want them to always grow. Otherwise, we'll collapse under our own weight and we'll be tripping over our third leg. So our body has an automatic way of telling our cells that they've done enough. You can stop growing now. Chill out, enjoy retirement, until you're needed again. But sometimes, something goes wrong in some cells. The instruction books might be damaged by things like smoking and too much sunlight. So the cells might not get the message and think they just need to grow and grow and grow. This turns the cell into a monster cell, like the Hydra. It can't stop, won't stop growing. It'll ask the body to give more and more of its blood and sugar and oxygen and whatnot, and it will even take up valuable space needed by neighboring cells to do their jobs. This is what cancer is. Cells that have gone rogue and won't stop growing. Cancer is a huge problem because it's really selfish and wants nothing but its own growth. So even if it means stealing blood from neighboring cells or eating into important organs like your lungs, liver, or even your brain, it just keeps growing. Sometimes the cancer even breaks off a piece of itself and leaks it into the bloodstream, so that the splinter cells can grow and grow and grow into their own tumor somewhere else in the body, causing even more damage. Eventually, the selfish cancer cells take over the body, upsetting the fine balance that lets it stay alive and kills the person. Because cancer is deadly, doctors try really hard to look for it early before it grows out of control and kill it before it does too much damage. But it's really hard because cancer is such an expert of surviving and growing, and there are so many different types of cancer because almost any type of cell in the body can go rogue and turn into its own unique kind of cancer. Even worse, cancer is technically still you. Even though it's a mutated, monstrous cell, it's still your cell. This means that we can't use medicines like antibiotics that can target cells that are very different to our own cells, such as bacteria. Whatever we use to kill cancer cells can technically kill your own healthy cells as well. But thanks to science, there are more and more exciting ways of treating cancer, and doctors are getting better at only targeting cancer cells while reducing the bad effects on the patient and their healthy selves. However, the best thing is to stop cancer from happening in the first place, to reduce the risk of cells and their DNA or their instruction manuals from being damaged and letting the cells go rogue. So, make sure you slap on your sunscreen, don't smoke cigarettes, and do all the screening tests your doctor tells you to do. Alright, so cancer is a very weird type of disease in that it's not something from the outside that is trying to kill you, like an infection or toxin or physical damage. It's your own cells going rogue and doing their own thing, which can result in death. So to understand what cancer is and how it comes to be, we need to first learn what happens when normal cells are growing and dividing. Every cell in your body technically has the ability to grow and divide. Technically. This is important because when you are first conceived, you start off as a single-celled organism, the zygote, created from a single egg cell and a sperm cell joining up to become one. This zygote divides into 2, then 4, then 8, then 16, until exponential growth takes over and you become a ball of cells, then an embryo, then a fetus, until you're born as a baby. Then you grow up in both size and maturity as you become an adult. Cells need to grow and divide for this kind of development to happen, but it doesn't stop after you become an adult. Cells are constantly dying or becoming damaged, either from day-to-day wear and tear or just getting old. For example, your red blood cells only live for 120 days before they're broken down. Your skin cells barely last a month before they're shed, while your brain cells essentially last your entire life. So, we need to constantly replace old and broken cells with new, hot, fresh cells. This is also the case for tissue repair and regeneration. If a part of the body is damaged, say a cut in your skin and muscle, or an infection eating away your lung tissue, your body is able to regrow the damaged portion to a certain degree. So, how do cells divide to become 2 cells? Without going into too much details, lest I trigger your biology PTSD by mentioning words like G2 phase and chromatin condensation, we can think of cell division occurring in 2 main phases. The first phase is the prep phase, also called interphase. This is when the cell gets ready for division. If you took a normal cell and split it in 2, you'd end up with 2 rather small cells. Also, you'd only have half the amount of DNA, which is pretty useless unless you're a sex cell such as an egg or sperm cell. Therefore, the cell needs to bulk up and double its DNA count before it's ready to divide, just like a gym bro bulking up with a high-calorie diet before he cuts. Next, the M phase comes along, when the actual division happens. In biology, this is called mitosis, not to be confused with meiosis, which is when cells divide without doubling their DNA so they can create the half DNA sex cells that we mentioned. Mitosis is an extraordinarily intricate process that looks like some kind of meticulous ballet of cell components. In a nutshell, the double DNA is packaged into chromosomes that look like an X. The chromosomes line up in the middle of the cell nucleus, and then they are ripped in half by teeny tiny cables that pull each half to the opposite side. The cell nucleus then pinches off to form 2 exact copies of the original nucleus, and then the rest of the cell cleaves in 2, with 1 half each containing a cloned nucleus, with the superpower that is cytokinesis. Now, once this happens, you have 2 cells that are the exact copy of the original cell, which means each cell can start bulking again before cutting and forming another 2 cells. Bulking and cutting. This is the foundation of the cell cycle, which governs cell growth and division. But as we've mentioned before, you can't always be growing. Just look at the economy and large businesses. If you only have aggressive growth, Something's going to give and it'll all come crumbling down. In the case of the body, this might mean you have an overgrowth of cells, meaning your organs will get too large. There'll be disorderly conduct, and the resource demand will be way too high. Eventually, you'll look like a giant sack of Cronenberg meat. So to prevent this from happening, evolution has ensured that life has a way to keep growth in check. When the body thinks cells in a certain area have grown enough, say because you've got a whole arm grown to the right size, it tells the cell to stop growing. Instead of continuing the cycle of bulking and cutting, the cell then instead enters a resting phase, where they become content with how shredded they are and live out their lives in bliss, until the order comes to start growing again if needed. The body also has some more extreme measures. If they detect cells that have grown too much, or they need to unalive some cells to make space, say the spaces between your fingers so you don't end up with webbed hands and feet, they can tell cells to self-destruct. Yep, it sounds hardcore, and the name of the process is just as badass: apoptosis. Cells can either be pre-programmed to kill themselves when they're no longer needed, or certain immune cells can tap on their membrane, send a secret signal, and the cell will automatically break itself down and burst like a bubble. This is really useful when the immune system detects cells that are infected with something like a virus, or if the cell is starting to go rogue, such as in the case of cancer. Apoptosis is also a very clean process because the cell breaks down very calmly and orderly, making it easy for the immune system to mop up the pieces, resulting in no inflammation. It's a normal part of life of cells, and crucial to maintaining proper cell growth and structure, while destroying damaged or infected cells without messy inflammation. Okay, now we get to the really interesting bit. We've learned how the cell cycle is tightly regulated, and the immune system can trigger apoptosis to prune and maintain order among the cells in the body. But as we've alluded to, this can go awry sometimes, and that's what cancer is. How does this happen? The most important thing to know about cancer is that it's rarely due to one thing. As we can see, the body has lots of different safety checks and fail-safes to literally prevent cancer from happening. So even if one thing goes wrong, say a cell forgets to go into resting phase and keeps dividing, another fail-safe like apoptosis can stop the cell from growing out of control like wildfire. Many of these fail-safes are programmed into the cell from birth, written directly into the genetic code, the DNA. Even though cells are amazingly complicated and intricate, they are, at the end of the day, still biological machines that just follow instructions. If the DNA tells it to make something, it makes it. If it tells it not to do something, it won't. Very obedient. Our DNA contains numerous genes that specifically tell a cell not to be cancerous, to make sure that its growth and division is regulated and kept in check. We call these tumor suppressor genes because they literally do just that. These genes may also code for proteins that help DNA repair itself in case of accidental damage. But as we know from disasters such as Chernobyl and the Titanic, no matter how many fail-safes you have in place, accidents still happen. And in the body, that accident is cancer. Cancer is usually the result of many different types of damage to the cell DNA that happens to line up perfectly so that the cell can grow indefinitely unchecked. These are called the hallmarks of cancer, and they're the characteristics common to almost all cancer cells. Let's look at them one by one. First, the cell is self-sufficient in growth signals. This means that the cell has its accelerator pedal stuck on, and it thinks it's being told to keep growing and growing without ever going into rest phase. Second, the cell is insensitive to anti-growth signals. This means that the brakes don't work, and the cell stops listening to the automatic "you've had enough growth, stop it" messages the body is sending. Third, the cell evades apoptosis, as in it ignores the immune system's request for the cell to commit Sudoku. Fourth, the cell gains limitless replicative potential, meaning that it can divide and divide without any consequences. Most cells are programmed to only divide an X amount of times, like having a limited number of one-up mushrooms and lives. Cancer cells don't have this limit, so they can grow infinitely, like they're using a cheat code. Fifth, the cell can sustain its own angiogenesis, a fancy way of saying it can lay down more blood vessels to feed it. As the tumor grows and grows, it needs more and more fuel and oxygen, as otherwise it would starve itself to death. More blood vessels mean more food for the cells. Lastly, the cells learn to invade surrounding tissue and can even spread to other parts of the body through something called metastasis. We'll talk about this in more detail later. All of these characteristics are normally kept in check, but if all of them fail at the same time, the cell can turn into cancer. There's also other hallmarks that are common to cancer cells, such as being able to generate energy in alternative ways, evading the immune system, and causing chronic inflammation. But the bottom line is, to create cancer out of normal cells, we need a lot of things to go right, or wrong, I guess. And yet, cancer is very, very common, especially the older we get. This is unfortunately just statistics. The older you get, the more you've lived, meaning your cells have had more time to possibly get one of its cell-safe mechanisms knocked out. This might be due to environmental damage, such as carcinogens and cigarette smoke and pollution, UV light and sunshine, or certain inflammatory foods such as alcohol. We've talked about how smoking and UV can cause cancer through DNA damage in episodes 53 and 62 respectively. It might be just random chance mutations, as DNA can make mistakes when it's copying itself for normal cell division. In some cases, people may have inherited something called oncogenes from their parents, genes that make a cell more likely to become cancerous. Some people may have genes that dial up the "you should grow" signal to certain cells to 11, causing unchecked growth. Some people might have faulty tumor suppressor genes, meaning that their DNA can't repair common accidents or damage, so they're more susceptible to having the fail-safe mechanisms knocked out. For example, I have something called Lynch syndrome, where one of the genes responsible for repairing DNA mismatch in my cells is defective, meaning that my rapidly dividing colon cells might not be killed in time if they contain dangerous DNA changes that might turn them into cancer. If you know someone who's had a BRCA1 mutation-related breast cancer, this is a similar situation, where their BRCA gene, or BRCA gene, which normally helps repair breaks in the DNA, is mutated and does not do its job properly, meaning potentially cancer-causing DNA changes are left unrepaired as the cell keeps dividing. So yeah, the cause of cancer can be quite complicated and difficult to trace to one specific cause, unless it's something like tobacco and sun exposure and certain shoddy genes, which we definitely know has a very high risk of causing cancer. All of these factors have to line up in the same cell, with each defense mechanism knocked out one at a time, until the cell loses all of the chains that keep it from becoming a bad boy and turning into cancer. This means that the best thing people can do to prevent cancer from happening is controlling the things that we can. We can't choose what genes we're born with, but we can choose what kind of risky behavior we undertake. For example, we know that ionizing radiation causes DNA damage in cells, so we shouldn't willy-nilly expose ourselves to radiation such as UV light and unnecessary CT scans to reduce the risk of cancer. We can also avoid smoking cigarettes, which is known to directly cause lung cancer, as well as various other malignancies such as head and neck tumors and throat cancer. But most importantly, we can look out for early signs of cancer, so that if some cells go rogue and start growing into cancer, we can detect it and eradicate it before it becomes a problem. So, in this next section, let's talk about how we can hunt for cancers. As we know by now, almost every type of cell in the body can turn into cancer. Skin cells, bowel cells, lung cells, brain cells, and even blood cells in the bone marrow. So, naturally, there are hundreds of different cancers. This means that there is no one magic test that can tell you whether you have cancer or not, but there are things we can look for. The biggest thing we look for is risk factors, because the more risk you have, the tests have a higher chance of picking up the cancer. This is why, to the dismay of every smoker, we ask everyone who comes to the hospital if they currently do or have smoked cigarettes in the past, because that's how dangerous smoking is when it comes to cancer risk. We also look at your family history. For example, the fact that all of my father, my uncle, my aunt, my grandmother, my cousin, and many relatives to my dad's side all have had colon, endometrial, or breast cancer is not a good sign for me. It suggests that there may be a genetic component that I have inherited, which turned out to be true. There's also occupational risks, such as people who work in hair salons and chemical factories having a higher likelihood of getting bladder cancer, and people who work in areas of high radiation having higher risk of blood cancers. On a broader scale, everyone has a risk of a certain type of cancer based on their sex, that is, the biological sex that you are born with according to your X and Y chromosomes, which is different to gender. Every woman has a risk of developing breast cancer, while every man has a risk of developing prostate cancer. The older we get, the higher the risk for these cancers become. So every man and woman is recommended to get screening tests for these two cancers as they enter middle age, earlier if they have other risk factors like a family history. Thanks to medicine, we have lots and lots of different tests now that can detect various cancers. These tests not only help doctors confirm a suspected diagnosis, but also help us root out cancers early, before people start showing any symptoms. The difference of finding a cancer when it's a teeny tiny lump of cells versus when it's a chunky mass starting to eat into the neighboring territory or even spreading to other parts of the body is huge when it comes to treatment and the outcome for the patient. So screening is extremely important. There's too many tests to go into detail, but they include tests such as mammograms that can look into breast tissue with x-rays, colonoscopies that can see budding polyps in the bowel, blood tests such as PSA that can look for hints of prostate cancer, and pap smear tests that look for cervical cancer cells. An important part of screening is physical examinations as well, such as a rectal exam for checking the prostate, breast exams, and testicular exams, the latter two which can be done by yourself regularly to look for suspicious lumps, then further checked by your GP or family doctor if you're not sure. As varied as the types of cancers may be, there are some common constellations of signs and symptoms that may lead a doctor to think about cancer as a potential diagnosis, especially if they fit the risk factor profile. So, for example, if a person with a 20-year history of smoking a pack of cigarettes a day comes into the emergency department coughing up blood, short of breath, and losing a lot of weight without being on a diet, we immediately get suspicious that they may have lung cancer. Of course, there are other possible diagnoses such as pneumonia, tuberculosis, or pulmonary embolism, but cancer is on the differential. Similarly, if a young person comes in with weight loss, low appetite, hard lumps on their neck or armpit, plus fevers and sweats at night, we might be suspicious for lymphoma. But at the same time, they may just have a simple viral infection. This is why if you're concerned about your health, you shouldn't ask Dr. Google or ChatGPT, you should ask an actual medical professional like your GP. We could talk on and on about the various ways cancers can present, but then we'd be here all day, so let's move on to what happens when a cancer diagnosis is confirmed. Just remember that the best strategy against cancer is prevention. So reduce your risky behaviors by quitting smoking, getting your HPV vaccine if you're a woman because it will drastically reduce your cervical cancer risk, and get regular checkups including prostate or breast exam. Okay, so say a person is admitted to hospital because they have a confirmed case of bowel cancer. What happens next? Obviously, there's a lot of pastoral care that goes into breaking the bad news and preparing the patient and their loved ones for the journey ahead. But, like I said at the start, we won't go into that part in too much detail. Medically speaking, the first thing we need to do is identify our enemy and determine how powerful they are. Much like how Vegeta and Nappa used their scouter to determine that Goku's power level was
"It's over 9,000! What, 9,000?"
We need to analyze the cancer. Most cancers, with blood cancer such as leukemia being an exception, come in the form of tumors, essentially poorly organized lumps of cancerous cells that are growing and growing. By the way, we call these cells malignant because they grow without any restraint, like a child let loose in a candy shop. In fact, while we're here, let's talk about some cancer lingo, because doctors are notorious for our technical babble. When we spot something on an X-ray or a CT that looks suspicious for cancer, we don't straight up say, "You got cancer," because the only way to confirm it is with a biopsy, where a small sample is taken and looked at under a microscope. Instead, the most common way we describe the suspicious spot is with the word lesion. Lesion is a very non-specific term for any kind of tissue damage or abnormal change. So a paper cut is a lesion. A brain tumor is also a lesion. Similarly, a lump is just a lump of tissue. It may be benign, which means not cancer, or malignant, which does mean cancer. Tumor is actually just a fancy way of saying lump, whether it's cancerous or not. The word mass is used in a similar fashion, but tends to lean towards describing cancerous tumors. Finally, the word neoplasm also means cancer. You'll hear words like carcinoma, adenoma, or sarcoma. These are all various types of tumors that may or may not be cancerous. My favorite is incidentaloma, which is what doctors call those pesky lesions that pop up on whole body CT scans when we weren't looking for cancer, we were just looking for liver damage. And now we're forced to look into it, even though it may end up being nothing but a calcification. Okay, so back to the biopsy. A biopsy lets the pathologist identify several features of the tumor that is very important for the treating team. First, is it cancer? If so, what type of cancer? Not all lung cancer is the same, because the lung is made up of many different kinds of cells. So you can have squamous cell carcinoma, adenocarcinoma, small cell lung cancer, and so forth. Pathologists can study how the cells look under the microscope to figure out what kind of cell it mutated from, as well as whether it has the hallmarks of cancer that we talked about, such as rampant unchecked growth, lack of apoptosis, self-regulated angiogenesis, or blood vessel production, and so on. The type of cell is important because some malignant cells are a lot more aggressive. This doesn't mean they're going around cussing at other cells and flipping tables, but more that they will grow more rapidly, causing a lot more damage to their surrounding and have the potential to spread. So these cancers might need more aggressive treatment, and time may be of the essence. We call the aggressiveness of cancer its grade. High grade means aggressive, fast-growing cancers, whereas low grade means the opposite. The next thing the pathologist can do is stain the cells with all sorts of things, which might yield lots of details about the makeup of the cancer cell. Some features, such as certain surface proteins or hormone receptors, might let us deploy very targeted medicines that will kill the cancer directly, which is very helpful. Once the biopsy is analyzed, the next step is to stage the cancer. And no, this doesn't mean we're dressing it up and making it put on a show. It means we're trying to figure out how advanced the cancer has become already by the time we found it. Like we mentioned before, cancer starts as a single, naughty cell gone bad. As it grows, it forms a tumor that grows and grows in size. Sometimes the cancer cells can specialize into different kinds of cells, so the tumor doesn't necessarily have just one type of cell. For example, teratomas are terrifying because the cells can differentiate into all kinds of things like hair and teeth. It's like the world's worst mystery fun bag. As the tumor grows, it needs more blood supply because it's a hungry hippo. So it sends out signals that tells the body to lay down more blood vessels that feed it. But both the tumor and the blood vessels that feed it aren't growing in an organized way, so they kind of get put down shoddily and can break or collapse, causing bleeding and other issues. But here comes the worst part. The tumor doesn't stop growing just because it's butting into neighboring healthy cells. Like, oh, excuse me, pardon me, let me just tuck that butt back in. Oh dear, how rude of me. No. The tumor actively pushes on surrounding tissue and goes as far as eating into the connective tissue that holds the area so that there's more space for it. For example, cancer cells can eat into bone and cause fractures because the healthy bone is replaced with tumor. In the brain, tumors can grow too much and cause high pressures, which can cause headaches, seizures, and coma. In the case of some cancers, such as ovarian cancer, there's nothing to push against the tumor, so it can grow to the size of a watermelon before it's discovered. Anyway, the last and most awful thing that cancer can do is decide that it's gotten too big for the town it's living in and start to franchise out to set up lots of shop elsewhere in the body. This is what is called metastasis, and it's the worst because instead of one tumor, you have to deal with several tumors all over the body. Worst of all, once you see a metastatic lesion, you can't know for sure that there aren't teeny tiny metastatic cells hiding elsewhere that aren't big enough for you to see it yet. This is why metastasis affects the stage of cancer. If a tumor is confined to its original spot, it might just be stage 1. This is great because a single surgery may be enough to cure the patient of cancer. Stage 2 is when the cancer is creeping into the surrounding area, like a rude airplane passenger sneakily claiming more of the armor space. This makes surgery more dangerous because the surgeon has to be absolutely sure that they've cut out all of the cancer and its spreading tendrils, so they need a wider margin of error when cutting. Stage 3 is when the cancer is advanced even more. By this point, the cancer may have already invaded the local lymphatic system, which is designed to drain away excess fluid and waste products. This means the cancer can hitch a ride to the local lymph node. If you've heard of someone with breast cancer having surgery on their armpits, this is what it is. The breast drains its lymphatic system into the axillary lymph nodes in the armpits, and this is where breast cancer spreads to first usually. But if lymphatic spread is like a criminal catching a bus to travel to the next town, there's a worse way of spreading that is akin to the criminal sneaking to the airport and catching an airplane. That's your blood vessels. Blood goes all around the body, so if the cancer can make it to one of the big blood vessels and break off some pieces, those cells can end up in really far away places. Common places that cancer metastasizes to are the bones, the liver, the lung, and the brain. The problem by this stage, stage 4 to be specific, is that the cancer might just have gone to the liver, but there's no guarantee that it didn't also go to the lungs or some other lymph node. Now, instead of hunting for the fugitive in one town, we need to do a global search, and there may be hundreds of fugitives now, so you can see how this is a big problem. This is the reason that once a cancer reaches stage 4, it becomes very difficult to completely cure. Instead, you might be able to get someone to a state of remission at best, where there is no active cancer seen on scans such as PET-CT that lights up any areas of the body that are unusually active, as seen in cancer cells. But there may be splinter cells of metastases lurking in teeny tiny spots that may eventually grow back and spread even more. Eventually, cancer kills you by either consuming all of the body's resources in a state called cachexia. The tumor starts crashing important organs such as blocking a bronchus in a lung to cause it to collapse, gumming up blood vessels to cause necrosis, or increasing the pressure in the brain so much that it dies. This all depends on what type of cancer the patient has and what kind of complications they've developed. But a large proportion of untreated cancers will eventually lead to death as they grow and grow without being considerate for the delicate balance of the body. Great. So on that depressing thought, let's take a break. And when we're back, we'll learn about how doctors treat cancer to fight back against it. Welcome back. We've spent the last while talking about what a depressing disease cancer is. It's literally a pile of self-replicating, mindless mutant zombie cells that eat away your body, sometimes even surprise attacking organs out of nowhere by sneaking into the bloodstream. So, what can we do to stop it? To reiterate, the best way to treat cancer is by preventing it in the first place, or rooting it out early through screening and risk mitigation. But what if the cancer has already put its roots down? What can we do then? In ancient times, such as the late 1800s, yes, modern medicine is a very recent thing, and you should be really grateful that you weren't born 100 years ago, or any time before that. All doctors could do then, against tumors, was to cut them out. And they would only be doing this when the tumor was becoming an obvious problem, like a giant lump in the neck making it difficult for the person to eat or breathe, or a mass that breaches the skin and oozing out in a disgusting process called fungation. Not fun at all. But like I said before, if you don't cut all of the cancer cells out, it'll just grow back, like the Hydra in Greek mythology. So before the invention of microscopes, where a pathologist could confirm by looking at the lump of flesh the surgeon cut out that all of the cancer has been successfully cut out in the wide margin, cancer survival rates were woefully low. Also, bearing in mind that receiving surgery back then was a very unpleasant experience due to lack of anesthesia and ludicrous infection rates causing death due to sepsis. However, in the last 100 years, we've come a very long way when it comes to the war against cancer. This means instead of having one option, we have many different kinds of treatment options available. And just like a healthy diet, doctors will often combine various treatments tailored to the patient and their unique cancer situation to best combat it. Broadly speaking, there are 4 types of treatments that aim to treat cancer: surgery, chemotherapy, radiation therapy, and other novel therapies that include hormone therapy and biological therapy. We'll talk about each one separately, but it's very important that you understand that these treatments aren't competing against each other, but cooperating. For example, the patient may be given radiotherapy first to shrink the tumor, which can then be cut out with surgery. Then chemotherapy is given afterwards to mop up any malignant cells that may be lurking. And finally, a biological therapy might be given to prevent any hardy remaining cancer cells from growing back. That's right, the real cure to cancer is teamwork. Okay, so we've talked a bit about surgery already and how staging and margins are important to ensure that all of the tumor is cut out. To facilitate this, we use imaging technologies such as CT or MRI to visualize where the tumor is and may have spread to, as well as stains and dyes to see what lymph nodes may be affected, so they can be biopsied on the operating table and checked for cancer as well, to see if they need cutting out as well. So let's talk about the two types of treatments that I'm sure you've been desperate to learn about today, how they work. Chemotherapy and radiation therapy. These therapies are extremely different in nature, but their goal is the same. Kill cancer cells while not harming healthy cells as much. In the case of chemotherapy, colloquially called chemo, a variety of medications can be used to kill cancer cells. This is because there are hundreds of different cancers and they all react differently to various medicines. But at the end of the day, most chemo agents are some kind of intracellular cytotoxic poison, as in, they kill cells. And if you remember, you're made of cells. So, how come you don't die while receiving chemotherapy? Well, awkward truth is, you kind of are. To an extent. Most chemo agents are what we call alkylating agents. They work by sliding into your cell's nucleus, bonding to the DNA, and forming bonds and crosslinks to prevent the DNA from being accurately read. If you remember our last month's episode on sunscreen, you'll remember that this is exactly how UV light can damage your cells and cause cancer. It's the equivalent of spilling syrup all over a recipe book. The pages get all stuck together, so you can't make the delicious baking that is life. When this happens, the cell may trigger apoptosis and destroy itself. If it doesn't, it still won't be able to grow and divide, so the tumor dies off. Now, here's the cool part. Because chemo targets the cell's ability to replicate its DNA and divide, it affects fast-growing cells first. And what hungry hippo really likes to grow? That's right, cancer. So chemo disproportionately affects cancer cells over healthy cells. That said, there are some exceptions. The cells that line your gut, your mucous membrane such as your cheeks, and the cells that grow your hair and the follicles are all rapidly dividing as well. These cells also get hit hard by the chemo, which is why nausea and vomiting, tummy upsets, mucositis, and hair loss are all really common side effects of chemotherapy. Sort of the equivalent of outlasting cancer in the see who can stay the longest in a hot bath competition. The other rapidly dividing cells that get affected are the cells in your bone marrow that make blood cells. This is why people having chemo are often immunosuppressed or neutropenic, because they're not producing enough white blood cells to fight infections. Chemo can also affect rapidly dividing sex cells in the ovaries and testes, which can unfortunately cause infertility in young patients. Depending on the chemo, there's all kinds of possible side effects, but the hope is that those are manageable, whereas cancer will definitely kill you. There's way too many varieties of chemo to go over, but the majority are platinum-based, which is another cool fact. When you get chemo, you're being loaded with platinum, which makes it sound a bit fancier. It's also a misconception that all chemo causes hair loss. Some agents, depending on the type of cancer, don't affect the hair follicles at all. Once the chemo does the job and stops cancer cells from dividing, the cells eventually die and the immune system mops it up, breaking it down and letting the blood carry it to the kidneys, where the cell remnants are excreted into urine. Or in layman's terms, as put so delightfully by the YouTuber, author, and now comedian Hank Green, who survived lymphoma recently, you literally piss out the cancer. Now that we know how chemotherapy works, explaining how radiation therapy, also called radiotherapy, is much easier. Essentially, we're doing the same thing as chemotherapy, but instead of using poisons, we use high-powered ionizing radiation to directly zap the cancer cell's DNA, causing breaks so severe that the cell can't repair it, leading to cell death. Yes, it's as badass as it sounds. When else can you say that your life was saved by a linear particle accelerator producing high-energy photon beams? That's some sci-fi come to life right there. The useful thing with radiation is that because of how waves work, you can arrange the radiation beams in such a way that it's focused on a specific point deep in the body, without damaging the healthy cells along the way. Kind of like how on a stage show, they can shine multiple spotlights on the main character while keeping the rest of the stage dark. The radiation dose is also divided up into lots of doses and given over a period of days, to reduce the damage to skin and other healthy tissue. Thanks to this, radiation therapy is relatively painless and low risk, but it can cause some side effects such as skin inflammation much like a bad sunburn, as well as damage to tear or salivary glands. Brain irradiation used to treat certain brain tumors can also cause some serious cognitive side effects such as fogginess, memory loss, and reduced IQ. One interesting thing about radiation is that although it is typically used to zap specific pinpoint areas to kill tumors, it can also be used to treat a type of cancer that involves no tumors, leukemia. Leukemia is a type of cancer that affects the bone marrow, where blood cells are made. This is why it's called a blood cancer. You can imagine an uncontrolled growth of bone marrow cells will cause it to produce way too many white cells, which can actually make your blood so thick that it can block arteries and cause strokes or cut off blood supply to other vital organs. It also suppresses other cells in the bone marrow, so you might not produce enough red blood cells or platelets, which can cause severe anemia and bleeding. But since it's not a distinct tumor and more of a blood cancer, we can't just zap one bone. Instead, we may need to do something called total body irradiation, where the entire bone marrow system is nuked with ionizing radiation to kill all the bone marrow cells. Then the patient is injected with bone marrow from another person with matching blood antibody types, which is what a bone marrow transplant is. The new bone marrow moves in and sets up shop to produce a healthy and balanced amount of blood cells. It's fascinating because this complex, risky, but ultimately life-saving therapy was developed in part because of the horrifying, deadly atomic bombing of Hiroshima and Nagasaki at the end of World War II. We talked more about nuclear fission and the nuclear bomb in episode 55 if you want to get back and learn more about it. Doctors and scientists learned that people exposed to large doses of radiation from the nukes had their bone marrows wiped clean, like a credit card exposed to magnet. Oh, wait, some of you listening might be too young for that reference. Like a cassette tape being wiped with a magnet? Nope, not that either. I'm getting old. Anyway, radiation and bone marrow transplant is essentially like wiping your computer clean and reinstalling Windows on it. Alright, so both chemotherapy and radiotherapy work by killing cancer cells more than they kill healthy cells. It still doesn't sound great, right? Kind of like burning a haystack to kill a flea, except the flea can multiply rapidly and kill you. Unfortunately, for a long time, these two were the best weapons we had, because cancer is you. In some twisted philosophical sense, cancer is still your cells, just gone rogue because its instruction manuals got damaged, and it's just following the wrong code and not listening to its manager to stay in line. To paraphrase Jessica Rabbit, it's not that cancer is bad, it's just drawn that way. It's just doing what life does best, grow and reproduce. In some ways, cancer cells are just trying to do what cells are initially born as, individuals, rather than cooperative members of a society. They're essentially just trying to form their own kind of life at the unfortunate cost of your life. So we can't use targeted therapies like antibiotics that only affect bacteria but not human cells. Or at least, that used to be the case. Enter biological therapies. Thanks to ongoing amazing developments in the world of biomedicine, there are now specific drugs available that can home into specific receptors on cancer cells of certain types and only kill those cells, like a homing missile for cancer. There's a variety of ways the drugs can do this, but they usually involve specific receptors or interfering with specific proteins that won't interfere with normal cells. We call this group of treatments biological because they tend to be custom-made antibodies. So we're taking a leaf out of nature's book. Oh, and speaking of nature, there's an even more exciting chapter of cancer treatment research, and that's immunotherapy. Because turns out, the best targeted cancer treatment that only kills cancer cells and leaves healthy cells is not some long-lost ancient medicine in a jungle or a cutting-edge molecule made with machine learning, but already inside us. That's right, it's our old friend, the immune system. The immune system is insanely complex, and we're still learning things about how it works in the modern era. Turns out, there's a whole facet of the immune system, specifically part of the innate immune system that is designed to sniff out and weed out cancer before it becomes a problem. This means that even though new cancer cells are being born constantly throughout your life, your immune system is keeping it in check by searching and destroying them before they become a tumor. Similarly, the immune system can detect cells that are infected with viruses and destroys them. But how can the immune system tell what cells are cancerous when we need microscopes and stains and trained pathologists? Do they look or smell different or something? Kind of. For this, nature developed a very clever system called the Major Histocompatibility Complex 1, or MHC1. This sexy sounding protein is found on the surface of all of our cells, and they act as a sort of window into the cell factory by displaying a sample of protein that the cell produces. The immune system constantly monitors what the cells are making, auditing and sampling the proteins displayed by the MHC1 on cells. So, if a cell is infected with a virus, it'll start producing viral proteins, which the immune system detects on the MHC1 and says, oh, no. We need to burn this bad factory to the ground. The immune system gives the cell a friendly little poke, sending it a suicide signal and triggering apoptosis. Boom, no more infected bad cell. Same goes for cancer cells. Remember those oncogenes we talked about where they can turn cells into cancer if they're turned on? These oncogenes make specific proteins that the immune system is actively looking out for, and when they're detected, they tell the cell to die to prevent it becoming a tumor. Okay, that's cool and all, but we've already learned that cancer can be sneaky, and the melting pot of DNA damage and mutations can cause it to have all kinds of superpowers. What if it accidentally stops making MHC1 so that the immune system can't see what it's making? And here's where we introduce one of my favorite badass parts of the human body, the NK cell, short for natural killer cell. No, seriously, I'm not joking, that's their scientific name. And they take nominated determinism to the max level because they're very good at killing. Natural killer cells have one job: kill any cell that doesn't have MHC1. So, if a cancer cell tries to be clever and hide, it gets killed by natural killer cells. It sounds like some Orwellian nightmare where Big Brother is constantly spying on you, and if you don't have your ID on you, you get shot on the spot. That's how the immune system do. So, what if we could hack into the immune system and jack up its power, or tell the immune system to look really hard at where we know the cancer is? This is exactly what immunotherapy is, borrowing or strengthening our immune system to specifically fight a known cancer. There are already exciting research projects and studies happening that are aiming to improve our T cell and NK cell functions to root out cancer, as well as teaching the immune system to better identify cancer cells by introducing certain proteins in the blood, kind of like a vaccine. One of the most exciting drugs currently is pembrolizumab, or Keytruda. The immune system has several off switches to prevent the cells from attacking healthy or important cells, such as the brain. Cancer can sometimes hijack the system by faking the signal, telling the immune system that these aren't the droids they're looking for. One of these switches is PD-1 on lymphocytes, and cancer cells can turn it on with a protein called PD-L1. Keytruda works by binding to the PD-1 receptor and prevents it from working, stopping the cancer from telling the immune system to snooze. It means that the immune system might kill some healthy cells, but because cancer tends to have more reasons to be killed, the immune system disproportionately kills cancer cells over healthy cells. But as powerful as the immune system may be, it's not perfect, because it may not kill all of the cancer cells. Natural selection kicks in, and the cells that had mutations that helped it survive keep growing and become better adapted, and eventually deploy many countermeasures to prevent the immune system from keeping it in check. And that's how cancer happens. So, researchers are diligently working on more novel, powerful therapies with fewer side effects to help set the balance back to our favor. There are also some hormone therapies as certain cancers respond to hormones to grow, so blocking the signal can reduce or even stop the growth. This is why some prostate cancer patients need chemical castration to block testosterone and arrest the growth of their cancer. By the way, we also can't forget an extremely important field: palliative care. Most people are under the false impression that palliative medicine is only for when people are dying. In actuality, palliative medicine is about improving the quality of life in people with any major illness, easing their pain, nausea, and other unpleasant symptoms, whether it be from cancer, stroke, or dying in general. You can see there are so many different factors involved in treating cancer, which is why I decided to do emergency medicine instead of oncology. But seriously, I think it's kind of cool that we live in an era where we are getting more and more tools to improve both survival rates and quality of life in patients with cancer, and I hope the future is even brighter. The success rate of cancer treatments can vary wildly, because there are so many factors involved. For example, some cancers are much more responsive to a certain treatment, such as certain testicular cancers being famously responsive to chemotherapy, to the point that you can even cure people with lots of lung metastases. The grade and stage of the cancer makes a huge difference, because like I said, stage 4 cancers are very, very, very difficult to completely cure due to the mets. Pancreatic cancer is a good example, where it often stays hidden until the cancer has advanced well into stage 4, because it doesn't cause any symptoms until the end of the cancer journey, where it all comes crashing down. Some small cell lung cancers can kill people within weeks of them being diagnosed. There's also things like the patient's underlying health conditions, whether their cancer has certain features that can be targeted by specific therapies, and whether a treatment is even available. A drug that can do wonders on a certain patient may be prohibitively expensive or not available in certain countries. So yeah, it's impossible to cover every facet of how cancer is treated in the hospital, but I hope this was a good enough summary that you'll at least now understand the many terms thrown around by doctors and nurses, what goes on inside tumors, how various cancer treatments work, and why we can't just invent a single cure for cancer. It's too complex. I note that we've once again passed the 9,000 words mark, so let's wrap it up there, and skip the 2-minute explain today. So what did we learn today? We learned how mitosis and cell growth works, as well as how cells can be regulated to stop growing, or even ordered to kill themselves through apoptosis. We learned that DNA in cells can be damaged by poisons, radiation, and even just accumulated age, which results in faulty cells. We learned that these faulty cells just want to grow and grow and grow, ignoring the body telling it to stop. This is cancer. We learned what various terms such as lesions, malignancies, and metastases mean. We learned that cancer is hard to treat because it's still a part of us, but the immune system is actually pretty good at identifying and destroying it. We learned that if the immune system fails to kill the cancer early, there are a myriad of treatment options available, such as chemotherapy, radiotherapy, surgery, and so forth. We also learned that there are exciting new research showing that immunotherapy can supercharge our immune system to fight cancer even better. Lastly, we learned that cancer is not just one disease, but an incredibly complicated field of diseases, with hundreds of different types. So, to cure cancer, we have a long way to go, because it's bloody hard. And yet, brave researchers all around the world are working tirelessly to create a healthier future. Well, that's it for today. Thanks for listening to Explain This. I hope you've learned something interesting and maybe even useful today. I try to keep the episode more focused around the medicine because I'm very aware that cancer is an incredibly sensitive topic for many people. It's why we're so careful as doctors with using the C word when talking about the differential diagnosis, and why I think it's very hurtful when people say something is cancer to describe bad or sucky things. Anyway, I'm looking forward to bringing some more lighthearted and fun topics in 2025. I'm focusing on another secret creative project this year, so I might try to make some shorter episodes, but apparently you just can't stop this man from talking. Hope you all had a happy holiday and a wonderful new year. If you're already struggling with your New Year's resolutions, why don't you go back and have a listen to episode 9 and learn about yearly themes instead. My theme for 2025 is the year of finally, where I'm finally going to work hard on 3 specific areas of my life that I've been slack about lately. Feel free to reach out via social media or email with your yearly themes, or if you have any personal stories about cancer you wanted to talk about. Or just come say hello. We'll see you next time. Bye for now. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter